Hey guys, how you doing? It's Coach Scott. So now we're going to do a review on our Unit 2 to get you guys ready for the test. And again, uh, lots of good concepts for expanding on our knowledge of the model of what stuff is made of. And remember, if you think that stuff are made of little particles called atoms, right? From Democritus, that's what he called things are made of little particles, called them atomos. We'll call them atoms. That's cool now. And we looked at a couple of things. One, how the movement of these atoms was transferred in a something that's hot because those balls were moving around real good into something that was, well, not hot, a thermometer, right? So then we talked about how movements were in gases. So let's think real quick. The most important thing we can see is what about these what about these gases, right? We did experiments in there. We looked at different graphs, and if I got it, ooh, that's really bad. But anyway, I cannot draw for squat with this thing. But if I've got a graph like this, we call that what? Okay, if it's pressure versus what? Think about it. Okay, if pressure increases, pressure goes up, then what does this do? It goes down. So of course that's volume, all right? And if we think about it, what is pressure? Pressure is the number of collisions against the surface of the container, right? The walls of that container. And if the um, pressure increases, all right, then the volume will decrease. Pressure increases, volume decreases um, because, well, those things are moving faster. We can draw little things. Think about what's going on here. All right, draw a little box and we'll put a little ball there. So those balls have more movement. There's more collisions. All right, all right. So volume goes down. Now as volume increases, all right. So volume decreased, pressure went up because there's more collisions. They're moving faster. Here, you've got the same number of balls, all right? And there's not that many. You've got bigger space there. I'm just going to redraw this a little quick. There we go. All right. So now we've got a bigger volume there, a bigger container. And let's say, I think I've counted 3 there. So now there's going to be less collisions against those walls because the volume is so much bigger. That's how we'd identify that. Another one of our little graphs we looked at, all right, and we say that, by the way, that is inversely proportional, all right, inversely proportional, 1 over V, okay. So as volume goes up, pressure is going to go down, all right. There's less collisions against those walls, all right. So if pressure doubles, the volume is going to decrease by 1/2. That's what the inversely proportional means. Now then we looked at another couple of them, and these all pretty much have the same graph here. And if you think about it, it's going to be a straight line, right, bisecting the origin, right, and any type of line like that, we say it is directly proportional, directly proportional. So we can say that about what? Pressure and the amount of gas. So I'm going to use N for the amount of gas. So then I can say if pressure doubles, then the amount of gas has to double if volume and temperature in Kelvin are constant, right? So if I add more gas, more N's, if I double the amount, then my pressure is going to increase because I've got more of the little balls, more of the little atoms banging around against the side of that container, right? So pressure is going to increase if volume and of course if temperature in Kelvin is constant. Now we've got another couple of little graphs here, and this would be the same thing for temperature in Kelvin. All right, pressure and temperature in Kelvin. All right, now if you think about that one, temperature in Kelvin is also got a good straight line like that. It is also directly proportional, all right, to pressure. Kelvin. All right, you should know how to convert to that. I shouldn't have to go through that and tell you again how to convert. It's 273, add it to Celsius, got Kelvin. Now, let's look at the pressure versus Celsius. Now, this was 0 Celsius, then our line's going to be right there. And we cannot say that that's got a good slope on it. And we do that again. I wish I had a nice handwriting, but I don't, sorry. So if I have a line like that, it's going to go there. Now my pressure, I've still got some pressure there. This means there's still some collisions. And again, why? Okay, when they created the Celsius thermometer, Mr. Celsius took a tube of mercury, put it in ice water, and he marked 0. Then he put it in boiling water, and he marked 100. And then he made a series of graduations between 0 and 100. Right? And that's how we get Celsius. It can get colder than that. And if it can get colder than that, that means that there's still pressure and there's still movement going on. Now, if you see these on the test, know how to identify which of these graphs go to which movement. So anyway, that's our first video. This is Coach Scott saying, Hullabaloo, connect, connect.